So we've learned how to classify our substrates. We've learned how to classify our solvent types. The rest of this flowchart is going to be looking at the difference between something called a base, something called a nucleophile. So next we need to talk about bases. And when we talk about bases, we're talking about it in terms of acids and bases. So let's look at what factors affect the strength of a base. In order to examine the relative strength of bases, we need to call back to the definition of acids and bases. By definition, the Bronsted-Lowry definition of an acid and a base is that an acid is going to be a proton donator, where a base is going to be a proton acceptor. And when we talk about a proton, what we really mean, what we really see in a solution is a hydrogen cation. So that would be an H+. This is just a proton floating around in a solution, and it's going to be quickly grabbed up by different molecules. So when we look at an acid, we're looking at something like hydrochloric acid. When I put hydrochloric acid into water, that will ionize into hydrogen and chlorine. What I'm really going to get here is H+ and Cl-. Now remember, these are both in aqueous solution. This is the proton I'm talking. In reality, this is going to go to a water molecule. So this isn't going to be H+. This is really going to be H3O+. That oxygen is going to pick up another hydrogen. But this HCl donated that proton to that water molecule. Okay? That water molecule, in this case, accepted the proton. So it acted as a base. Now, if I have something like sodium hydroxide, NaOH, and I put that into a solution, I'm going to end up with Na+, which is really just going to float around. It's not going to do much. But I'm also going to have this hydroxide anion. That hydroxide is going to see things like this, and it's going to be really hungry for that proton. It's going to snatch that proton away from that, this is a hydronium ion. It's going to snatch that proton away from the hydronium ion. So hydroxide is a very strong base. H3O is, by definition, an acid. This is what we're looking at. So this, in this case, would donate the proton, and this hydroxide would accept the proton. So this OH- is a base. So we should be able to see what's an acid, what's a base, what's getting the proton, and what's giving the proton. And with that in mind, we can start to make some general assumptions here. If we have a molecule that is not able to be stable with a negative charge, it's going to be really quick to pull a hydrogen off of something else, to pull that proton off of something else. And so it's going to be a stronger base. So the less stable something is with a negative charge, the stronger it will be as a base. Right? That is the first big point that we need to keep in mind. So if I look at something like H2O, well, let's look at it this way. Let's start with H3O+ to H2O to OH- to O2-. As I have these written here, going this way, the strength of the base increases. So going this way, my base strength will increase because that negative charge is increasing. So base strength is always going to be increasing with a negative charge. Now with those negative charges in mind, we're able to look at our first periodic trend for base strength. This is going to be going between left and right on the periodic table, and we're just going to look at 4 atoms. We're going to be looking at the nonmetals in the first row. So this is going to be carbon, nitrogen, oxygen, and fluorine. Now, if you remember back to general chemistry, we have a periodic trend for electronegativity. Fluorine is going to be the most electronegative atom. And because of that increase in electronegativity, so we've got an arrow going here, this is electronegativity. Because of that increased electronegativity, as I go to your right, to the right on the periodic table, the atoms are going to be better at sustaining that negative charge. So fluorine, if each of these becomes negative, so if I've got a C- N minus, an O minus, an F minus. Fluorine is much happier than any of these other atoms to hold that minus charge. It's got a high electronegativity. It's very good at keeping electrons close. And so because of that, F minus is more stable than O minus. O minus is more stable than N minus, and N minus is more stable than C minus. So what we're going to have here is base strength will actually increase going to the left on the periodic table. All right? Now, we're not going to run into just a carbon atom as a negative anion, or a nitrogen, or an oxygen. What we're going to run into, very frequently, is going to be those atoms bonded to hydrogen. So I'm really going to be looking at a CH3 minus, an NH2 minus, an OH minus, and F minus all on its own. So that's really the types of bases that we're going to come in contact with. We'll see CH3 minus, we'll see NH2 minus, we'll see things like that, especially hydroxide. This, when we're talking about acids and bases, this is kind of the star of the bases, all right? So this is base strength increasing going to the left of the periodic table. Let's take a look at point number 2. So our next trend is going up and down the periodic table. So let's use the halogens for our example here, because we're going to have the most halogens in the nonmetals in this case. So we've got fluorine, chlorine, bromine, and iodine. Now, when I'm looking at these, in solutions, I'm often not going to have these pure elements. I'm going to have the anion version. So let's go ahead and give each of these that minus charge. Now, with base strength going to the right and to the left, we're really looking at electronegativity. So our first guess here could be that we're going to have a stronger base going down because iodine has lower electronegativity. But that's not going to be the case. We're going to have a trend based on the atomic and ionic radius of these atoms. Each of these atoms is going to have another shell, another electron shell, a bigger electron cloud. And because of that larger electron cloud, it's easier for those negative charges to hang out. They're going to have more space to spread out. So fluorine might be just a tiny little point, and it's a very small radius. Chlorine might be a little bit bigger. Bromine, quite a bit bigger. And iodine is going to be huge. And because of this size difference, the negative charges for an iodine anion are going to be able to really spread out and stabilize. So because they're able to spread out more, they are able to stabilize more. With fluorine, they can't really go anywhere, so they're not as stable. So base strength is going to increase as we go up the periodic table. Okay? So this is all coming back to the ability to stabilize that negative charge. Now, before we hit point number 3, let's look at some different examples. I've got a few different molecules drawn up here. First, I've got H2O, water. Then I've got ammonia. And then I have methane. All versus the hydroxide anion. Now, I mentioned earlier, the hydroxide anion is kind of the star of bases. And that's going to be because it's very good at picking up a proton off of another atom. But didn't we say that there was a periodic trend going to the left on the periodic table? Wouldn't this nitrogen have be a stronger base than this hydroxide because N is more to the left than O? We're going to need to factor in that they are the same charges. So when they are the same charges, nitrogen will be a stronger base than oxygen. Likewise, if I were to put NH2 minus up here, that would be a stronger base than OH minus. But we're really not going to commonly run into an NH2 minus. Okay? Ammonia is one of the best known weak bases. So it is fairly basic. It does have good base strength. And that's because it has this lone pair that is pretty good at picking up a proton. It's going to want that extra proton. It's going to be better at picking that up than this oxygen is going to be. And so because of that, this ammonia is actually going to create some hydroxide anions in solution. But the CH4 molecule, notice it doesn't have any lone pairs. There's no space for this carbon to pick up a proton. And so at this point, at this charge, that carbon isn't really going to be doing any base reacting. So we need to keep some of those, what we would call in more advanced chemistry common sense, but at beginner chemistries, this might seem fairly foreign. We need to keep some of those things in mind. So all of these trends we're going to look at are going to be impacted by that charge. It's all going to come back to that ability to balance a negative charge. Okay? It's all going to come back to stability. The last trend we want to look at is our most exact trend. And this is going to be involving something called the pKa of an acid and a base. In order to understand pKa, first we need to understand the relationship between acids and bases. Because we have these things called a conjugate acid and a conjugate base. So let's take a look at those. If I've got something like hydrofluoric acid will go into water, and some of it will deionize, and some of it will turn back into hydrofluoric acid. And so I'm going to be making some of these hydronium ions and some of these fluoride anions. So some of these fluoride anions are going to want to take back one of those protons. And so because this F minus is going to be taking back a proton, while over here, this fluorine gave up a proton, this fluorine, depending on the situation, could act as an acid or as a base. So we need to fall back on that definition. Acid is going to be a proton donator, a base is going to be a proton acceptor. And so the term we use for this is a conjugate acid and a conjugate base. We're starting with HF, so this is the acid. But when we go and become F minus, now we become the conjugate base. So it's like the fluorine changed forms. It changed sides. It switched teams. Went from an acid to a base. So now it's going to act like a base. So when we're looking at things called weak acids and weak bases, these are going to be acids and bases that don't completely ionize in solution, that they'll have some of this back and forth. Something like hydrochloric acid will fully ionize. That negative chlorine anion, that's not going to pick up a new hydrogen. It's going to stay as a chlorine anion, okay? But fluorine here, that's going to want to pick up that proton again. So we have some of this back and forth. We can have a forward reaction and a reverse reaction. And depending on how quickly each one happens, we will reach an equilibrium at some certain ratio. Now we're able to find that ratio using this equation. We call this K. K is an equilibrium constant, and A, for acids, is going to be equal to the concentration of my products multiplied together divided by my reactants. Now, we aren't going to need to do this math. We just need to understand where it's coming from. So I've got concentration of H3O plus times the concentration of F minus divided by the concentration of HF. Now, we don't use the concentration of H2O because there is no concentration. It's a liquid. It's not dissolved in itself. It is itself. So we don't need to include that here. Because we also have the same amounts of both of these, we've actually simplified the expression. And so the Ka expression for an acid is really going to be, since these are going to be the same number, we're going to square our hydronium concentration. So I can say it like this. H3O plus squared divided by my original acid concentration. And when I do that, I get some certain value for Ka. It's really just an expression of what is the ratio of how much this is going to ionize, of how much this is going to break up, of how much this is actually going to be donating those protons versus how often is this conjugate going to be picking them back up. Okay? So we can kind of think of it like we could grade toddlers on how well they are at cleaning up their room. They take all their toys out of their toy chest, and sometimes they put them back, sometimes they take more out. What's our ratio of putting away to leaving it on the floor? Something like that. So once we have that Ka, we have a huge range of values for different acids. We can have everything from 10 to the negative 50 all the way up to 10 to the positive 45. We have a huge range of possible values for Ka. And so just like when we're finding pH, we're going to use a logarithmic function to make a more agreeable scale from 1 to 14, from 0 to 14. We can do the same thing with these Ka values. And so we can take the negative log of our Ka, and that will give us a pKa. So that's where we get this pKa from. The pKa is not going to be an exponent. We're going to have a number kind of on the order of negative 20 up to around 60. That's going to be kind of a range of pKa values. That's a lot easier to compare and contrast. That's why we do this. So once we've got those values, we can use them to judge the relative strength of an acid or a base. So because each of these is going to form a conjugate base, the higher this number is, the more that conjugate base is going to push back into being an acid. Okay? The stronger that base is, the more readily it's going to accept a proton, the more it's going to push back to the left side of this reaction. So that's really what's happening here. But all you need to take away from this is that as the pKa goes up, the strength of the base goes up. And so we have a table of pKa values for common functional groups like carboxylic acids, for alcohols, for amino groups. So we're going to be able to look at that table, look at our relative pKa, and identify if this is going to be a strong base or not. All right?